You just watched a video of a mountain biker bombing down a long downhill, and you probably asked yourself, I wonder how fast or what the speed was from top to bottom. So we can go ahead and do a velocity calculation here. We should probably, first of all, note that friction here is going to play a big part in how fast this rider is going to go down this hill. And because friction is a non-conservative force, we want to eliminate it from our calculation right now. So we're going to assume that this is a frictionless event. We know it isn't, but right now let's just not give any consideration to the friction involved in this and calculate velocity just simply based upon the law of conservation. And we know this as let's go ahead and track the course. First of all, a mountain biker is going to follow roughly this orange path down the side of the mountain, and this distance is certainly measurable, and we'll introduce that measurement in our next story problem. But for now, that distance is not important to our solution. We are not concerned with the distance that the mountain biker is traveling. What we are concerned with is something called vertical displacement. So vertical displacement is simply the top to bottom height from the top of the hill straight down to the bottom of the hill. And in our story problem, let's make that 105 meters for our vertical displacement. So again, the distance is not going to play a part in our first story problem, but the vertical displacement is very, very important. All right, so let's write down a couple things that we know and go ahead and solve the problem. One of the first things that we should probably write down is the fact that regardless of how the mountain biker got up here to the top of the trail, whether he took the long, torturous trip up the mountain on his mountain bike or he hopped a helicopter like we saw in the video, we know that he has a significant amount of potential energy up there at the top. And potential energy is calculated mass, gravity, vertical displacement. And we know that the law of conservation suggests that our potential energy should be converted to kinetic energy and friction, obviously, as we turn around and head down the mountain. So let's go ahead and set that up. We know that kinetic energy can be calculated 1/2 mass times velocity squared. So if we couple these two equations together, again, not considering the friction involved right now, we can see that mgh is going to equal 1/2 mv squared. Again, because of the law of conservation, our potential energy is going to be equal to our kinetic energy. And up to this point, we haven't really talked anything about the mass of the bike plus the rider, and you probably can see why. If you look at the equation, mass is present on both sides of the equation, so it's going to cancel out, and we're not going to have to give it any consideration. So our calculation for finding our velocity is going to be found by using GH is equal to 1/2 velocity squared. Okay, let's go ahead and substitute in what we know and solve this problem. Let's change our color to neon green and go ahead and solve the problem. So we know that our acceleration due to gravity is 9.8 meters per second squared. We know that our vertical displacement is 105 meters, and that is going to be equal to 1/2 velocity squared. To get rid of our 1/2 here, we're going to multiply both sides by 2, so it ends up looking like this. 2, I'm going to omit the units for the time being, speed up my video here a little bit. 2 times 9.8 meters per second squared times 105 meters is equal to velocity squared. To get rid of our square here, we're going to take the square root, so that sets up to look like this. Square root of 2 times 9.8 times 105 is going to be equal to velocity. And that will be in meters per second. If you do the calculation here, find that answer to be approximately, and we'll just use two significant digits here, 45 meters per second. You want to go ahead and stop the video right here and let students calculate this in maybe a more understandable speed, maybe miles per hour. This would be a good time to do so. I am going to write the answer now. That's going to equal approximately 97 miles per hour. Now, that may sound like he is really, really bombing down the mountainside. And you'd be right if he was traveling 97 miles per hour. Now remember again though, we did not give any consideration to the wind resistance and kinetic friction that's involved in this story problem. But if this was a frictionless event, we would anticipate that his speed down the mountain would be approximately 97 miles per hour.